Welcome back to the lab. One short year ago, something really cool happened on EEforEveryone. We launched a new series. We started working on the latest version of our little UPS project. Actually, that project is still going on strong, and we've talked about it quite a lot. Thankfully, that project is in a really exciting place. We're doing our final analyses. We're cleaning up the architecture. We're getting ready to actually build it. Get subscribed if power conversion or uninterruptible power supplies gets you excited. This thing is going to be beautiful. The UPS will be beautiful, but unfortunately, our work won't be very fun to watch. What we need to do for the next couple months is pretty boring. Actually, it's a lot of doing the same thing, very meticulous work over and over and over again. So here's the plan. I looked for a problem in our world. I looked for a problem that I could solve in a couple days. I looked for a problem that solving would take some suck out of the world and replace it with a little bit of awesome. I want to provide an opportunity to walk through the types of circuit analysis we'll be applying to the UPS, but using a smaller project as an example, which will teach the same principles but not get bogged down with how big that UPS system is. We've got a good backlog of projects filled with fun motor controllers, electronic loads, all sorts, colors, and kinds of things we'd like to build, but most of these projects, they're going to take a fair bit of effort to do right. And I wanted something that would be a little more simple, a little simpler. And that's why we're building a thermal runaway watchdog that will make 3D printing just a little bit safer for everyone. Meet Seth, the thermal runaway monitor. Now, every great project starts with a problem statement and an objective statement. If we don't have a problem that we're trying to solve or an objective for the project, what's the point? So here's ours. The problem that I want to solve is that currently existing thermal runaway watchdogs, both the ones built into 3D printers and external ones that you can build and add to the existing 3D printer, they don't sufficiently reduce the risk of fire while printing unattended. Now, I truly believe that most printers rely on a single point of failure for heater control, a MOSFET or a solid-state relay, the failure of which will likely cause heat to be constantly applied to the hot end or heated bed until the mains cord's unplugged. In the case of a heater FET failure, there is nothing that can be done in software. There's no replacement for being physically present and turning off power or unplugging it because software's already tried to turn off the FET, but it's stuck on. Now you might be thinking to yourself, but EEforEveryone, what about smart outlets and this great project posted by Artsuhao, maybe, on extractables.com? Well, first of all, great work. Way to put this out there. Way to build a solution to a very real problem. You recognized a risk. You went for a solution. But here's my hang up. Failures were considered in the 3D printer. I mean, that's why we're building this project in the first place, right? But I'm not convinced that failures were adequately considered in the monitor itself for that instructable. After all, this circuit does nothing until the heater MOSFET has already failed. If Seth failed to cut power to the printer when thermal runaway is detected or should be detected, your house is burning down. The system relies on software running on an Arduino, an off-the-shelf, hopefully mains-rated, hobbyist-grade relay being connected to mains, and those two elements of this system, for lack of a better word, sketch me out. They make me very uncomfortable. See, relays commonly fail in two states, either welded shut or permanently open. This can happen when switching mains because even with gold-plated contacts, sparks are flying when you make or break contact. If there's voltage across it, those sparks or arcs, that means that your contacts might occasionally weld together. And this happens more often than I'd like. If our relay is welded shut and the temperature monitor de-energizes the relay coil, that's great, but your house is still burning down. Gold star for effort. Oh wait, all my stars just burned up. Never mind. The audible alarm that you've added to this project is excellent if you're home, and I really want something that will bring me peace of mind. I've got to say, ever since I started thinking about this project, I've been very nervous about my 3D printer. Thinking about all the ways it could catastrophically fail and destroy all your stuff is a great way to add some anxiety to your life. 0 out of 10, would not recommend. Needless to say, I don't want to rely on software, I don't want to rely on the internet, and I'm building this thermal runaway monitor as a public declaration that I would rather have the nuisance of a failed 3D print than a catastrophic failure that leads to destroying a large value of things. I would rather spend $50 building a fault-tolerant, properly isolated, serious solution for this serious problem. A $10 cobbled together dev kit is great for a proof of concept, and being totally honest, that will probably work sometimes. But that's not what we're doing here. That's not EEforEveryone. I'm betting that this Instructable has prevented a couple fires. I'm guessing this has done some great work. I love that this exists, but it's simply not good enough for my house. I'm just as scared of being electrocuted by that relay module as I am of my 3D printer burning down the shop. Okay, that was one heck of a problem statement. How are we going to solve it? Now here's my objective. I want to design, build, and make publicly available a thermal runaway prevention mechanism for the hot end and heated bed of a 3D printer that is, in itself, single fault tolerant such that the failure of any one component in the system either has no impact on safety or causes the system to fail into a safe state. 3D printers should never be left printing unattended, but even if your printer's in another room or in your basement, fires get out of hand really quickly. I forget the exact statistic, but I believe that a house fire can escalate from no problem at all, just blow it out or get a blanket or something, to just run, this house is coming down in 15 minutes. That means that every 15 minutes, you should probably be running into the other room to check on things. And even if you're home, I doubt that you're really doing that. That sounds like a lot of stress and a lot of work. It would bring me great peace of mind to know that there's a fault-tolerant system keeping an eye on things that will respond in a millisecond or second timescale if something gets out of hand. Sure, maybe this thing will glitch out sometimes and ruin a couple prints. Whatever, no problem. We can always make a Rev B, a version 2, whatever we need to do to reduce nuisance trips, but I'm erring on the side of safety. Fair warning, this project, Seth, this temperature monitor, it's going to be expensive. This will not be the cheapest thermal runaway monitor in the world, but if I have my way, this will be the safest thermal runaway monitor in the world. And over the next few weeks, I'm going to explain exactly why this is the safest thermal runaway monitor for 3D printers, and hopefully make it accessible to you. All right, let's get there. How are we going to build the best thermal runaway monitor in the world? Well, it starts with great components. So I want to share a couple critical components that we'll be using to serve as the basis of this design. The first one, in my opinion, is the most critical, our relays. We'll be using the ALZ 12F12 from Panasonic, a 16 amp rated relay with 10 millimeters of creepage and clearance internal to the part and 12 external. This relay is capable of breaking 240 volts AC with the dielectric withstand and safety agency approvals to match. We'll be using one of these to break line and one of these to break neutral. The only connection that should remain to the 3D printer after the monitor trips will be earth ground unless one of the relays has already failed. Another critical component is the power entry module. We'll be using a power entry module with built-in fuse holder from Qualtech. This will provide some much needed protection against overloading the traces on this PCB or the relays themselves. The partner module, the 710W-00/3, also from Qualtech, is the power output connector, and this is commonly used for power distribution units or PDUs. These connectors are cheap, work great, and they're an industry standard for devices that switch mains to downstream devices. Perfect. Everything touching mains, our board included, we'll use 1/4-inch spade terminals with crimp connectors, no problem here. So that's the mains power path. I mean, if there's something unsafe there, there's no way this device can be safe, and I'm confident that is a well thought out power path. Another critical part of this system is how we're actually measuring temperature, right? I elected for a Type K thermocouple. Why did we pick a thermocouple? Well, first of all, fault detection is very easy. A thermocouple is normally a short circuit between two different metals, where the difference in the metals produces a voltage cross them that depends on temperature. So if the thermocouple isn't a short circuit, or almost a short circuit, then something has gone wrong. This is very easy to detect. We'll need something that will interpret that thermocouple, and that's what we're using the 8495 from Analog Devices for. This part is not cheap, but it is one of the most critical parts of the system. The temperature monitor on a thermal runaway prevention device is not the place to cheap out, and this IC should be an absolute great part. Linear voltage output proportional to temperature, cold junction compensation built in, ESD protection built in, and a thermocouple failure reads as Vout max, which ends up being 1000 degrees Celsius. I'm betting that'll trip our threshold. The last part that I'd like to highlight today is the thermocouple interface, which ends up being critical to noise rejection. A dodgy connection to our thermocouple will lead to false trips, which will ruin prints, so no expense was spared here either. We're using a great board mount mini thermocouple probe connector, the PCC SMPK. Absolutely great stuff. So these are the puzzle pieces that we will be arranging and interconnecting to build a fault-tolerant system. Speaking of, I'm really excited to walk through how we're going to use these critical components to build this fault-tolerant temperature monitor, and I really think this project is going to do some good in this world. I'm excited to share the analysis that we're going to do in the circuit to prove that it will meet our objective and solve this problem. We'll be diving into an analysis of fault tolerance, considering how individual component failures will impact the larger system. We'll also be considering power on transients, calculate a worst case error budget for the system, calculate accuracy of some comparator thresholds with hysteresis, and walking through how we're going to shape the physical implementation of this design to ensure that we aren't adding more problems than we're solving. Basically, we're going to dive into all the non-idealities of the system, we're going to think about these imperfections in the system, and we're going to make sure that this design will really work. We're going to make sure that this temperature monitor is safe all the time, every day, no matter if we build 1 or 1 million. If you buy one of these things down the road, I want you to have some peace of mind that it was designed well, it's well thought out, it's going to protect against 3D printer thermal runaway. That's all I have for today, but I'm really excited for what's next. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we'll be digging into comparators and voltage reference selection. I can't wait! If you want to support the channel, consider checking out the products that we featured today through our Amazon affiliate links in the description. It really helps us out a lot. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone. Thank you for staying till the end. Bye!